Hello, class. This will be the second of the 2 recorded lectures for section 7.2. And this is going to do calculations. Let's see, hit the right button here. Using norm.inv. And so what this function allows you to do is, given a certain probability, or percentile is also used as well, find the data point that fits within there. Now, this is different in the sense of what we calculated from chapter 3, I believe, when we were talking about quartiles and percentiles and all that. This is an exact value, more algebraic than what we were doing with those specific formulas that we introduced to you in that chapter. I find this to be a better calculation personally, because again, it's more algebraic. But I am teaching a stats class, so I do have to realize that the statistician's way is also important. So again, the way that the book described this, I found it very confusing. So I think the best way to do this is problem 14 or example 14 from the Alex homework. And it's a really good one. And I've modified it some to make sure that we have had a chance to do all the calculations needed and show you the concepts on the bell curve as well. I think that's really important. So this one says we have a mean of this manufacturing process where you have ball bearings. And so the mean of the ball bearing is 25.1 millimeters, and a standard deviation that's real small, which is a good thing. You don't want this huge standard deviation because you would get a lot of ball bearings that aren't by the mean, and that would not be a good thing. And so let me show you what this bell curve looks like. And so if that's the mean, we said M is 25.1 and the standard deviation was 0.04. So it won't let me just erase part of that line. So let me start over. Try to get a better bell curve here. Let's try one more. Oh, that's way better. Okay. So here is 25.1. And remember, that's a z-score of 0. And so if we go up 1, we're going to add. So that would be 25.14. We go up 2, it'd be 25.18. And if we go up 3, that would be 25.22. So if we go the other way, we subtract, that would be 25.06. Go down here, that would be 25.02. If we go down here, that would be 24.96. No, 98. And remember, that's a z-score 0, 1, 2, 3. And this would be -1, -2, and -3. Okay, so let's walk through these calculations. So going back, let's do the first one. So this says, find the 40th percentile of the diameter. It's like, okay, so what does that mean? Well, let's go back to our graph here. And first of all, remember that, let me put this in red, here's the 50th, right? That's right in the middle. So the 40th would be somewhere, just less than that. So you definitely want a number that would be less than the mean and definitely greater than the z-score of -1 or 1 standard deviation down. So I find the best way to do this is to use the spreadsheet with the INV calculation. So you go up to function. And now we bring up INV now instead of DIST. And so here you have 3. And so probability is in decimal between a 0 and a 1. And so the 40th percentile is 40th probability, 0.4. And then we have a mean of 25.1 and a standard deviation of 0.04. So the number is 25.0899. So you could see it's less than the mean, but bigger than that first standard deviation. So if we copy this here, let me stick it in my presentation here for you guys before I upload it. And that would be equal. And if I go back to the spreadsheet, I could get the number for you as well. And here we go. And so if we go back to our whiteboard, and you could see, so this point here would actually be 25.899 right there. 0899, sorry. Try again. 25.0899. Forgot my 0. And so you can see it fits right there. So that's physically the point. And so again, it gives you the exact algebraic value of the 40th percentile, which I find really good. Okay. So hit clear. Let's get rid of this. So the next problem it's not hard, but I just want to make sure you understand what these words mean. So the next one says find the third quartile, right? Third quartile of the diameters. And what is the third quartile? Well, remember, we would split this up into 4 quartiles. So quartile 1 would be somewhere around here, and that would be 25%, right? Or the 25th percentile. And the third quartile would be the 75th percentile. So when you do this calculation, what would be the probability we plug in? 0.17. So don't let those words kind of mess you up with regards to what you want to do in the calculation. So going back to the spreadsheet, we would pull up, and get into a different cell. That helps. And we put more functions, norm.inv. And then here we put 0.75. A mean of, what was the mean? I forget. Hold on. Let's see what the mean is. 25.1. Back to the whiteboard here real quick. There it is. So the mean is 25.1. Sorry about that. But you got to put in the right numbers or it's not going to make any sense, right? So let me write this down here so I don't forget. 0.04. We go back to the whiteboard, or sorry, the spreadsheet, and more functions start over. Okay, so probability is 0.75, mean is 25.1, and standard deviation of 0.04. And up comes 25.1270. So we could copy and paste that into our presentation here. So you have that as reference as well when I upload it. And that would equal, go back to the spreadsheet, copy that number, and that would be the answer. And so when you go back to the whiteboard here, you see that this point here would be 25.1270 right here. Very cool. Okay, so the next one states you want to find the middle 90th percentile, the middle 90%. So if you think about the middle 90%, all right, let's say, okay, here's the middle 90%. So you want to find the upper point and you want to find the lower point. So remember symmetry, right? So what's left if you subtract 100%? 10% is left, right? So in symmetry, you have 5 above this and 5 below this, right? And so to find the lower point, that one's the easier one, right? Because you're using 5%. So the probability that you would plug in at the norm.inv would be 0.05. That'll give you this point right here. So let me go back to that. And so I jumped to part D. We'll get back to C in a minute, well, after we do this one. So this is the lower one. So I'm going to type in the lower one. Just call it lower. And so this would be more functions, inverse, 0.05 for the probability, the mean of 25.1, and standard deviation of 0.04. So up comes the number 25.03 and some change, right? So if I copy that and stick that in the presentation for you guys, the lower would be this calculation, and that would equal this number right here. So if you went back to the whiteboard, I know it's a lot of clicking here, but I think it's worth it. This number here is 25.03421 diameter. So how do we find the upper one? Well, the upper one is what is the probability all the way down here? That would be 90 plus 5. So that would be the 95% one. And so when you do that calculation, you go back to the spreadsheet. And you do the upper point, and that would be more functions, inverse, and that would be 0.95. That would be 25.1, and that would be 0.04. And you would see you get a number of 25.165. So a little monotonous here now. Hopefully you're like, oh, I'm doing all right with this now. So let me copy and paste this here for you. So this would be the upper. And paste that in there, and that would equal, go back to the presentation. And copy that number there. Stick it right in there, and away we go. So going back to the whiteboard, the upper value here should be much bigger than the mean, and it is. It's 25.16579. So the last problem, I will get to it. Okay, so I erased all the last problem here, and we're going to do, I think it's part C here, but I think this is the trickiest of the bunch, so I left that one for last. So this is the idea of a hole is designed so 3% of the ball bearings will fit through it. So we would consider that a failure. So 97% of them are going to pass and 3 of them are going to fail. And when they fail, they're going to melt them down and remake them. And so they want to design this test fixture. I feel like my engineer again, where you would just have all the ball bearings go through this test fixture with a hole. And if it fits in that hole, it fails. If it doesn't, then it passes. And so the idea is, what is the diameter of that hole? So let's go back to our graph here and think about this for a second. So if we go back to the graph, we're looking at 3%, right? So that means 95% of these ball bearings are going to pass and not fall in the hole. So if you think about it, we're looking at a value somewhere down here where 3% of the ball bearings fall into the hole. So the question is, let's make the hole size that ball bearing would be. So how would we do that? Well, again, we need to get that point or that size of the ball bearing. And so it's just less than 3%. So we would go back to norm.inv in this case. And so this should be the last one of these. Probably getting sick of this. So when we do this calculation, we get to 3%, which is 0.03 in decimal, mean 25.1 again, and the standard deviation of 0.04. Cool. So that's the size of the hole that we would want to make that to do a test fixture, right? To get at the ball bearings that what we're considering to be too small to pass this test. And so let me just copy that for you and stick it in the presentation. Copy that number and away you go. So last thing I want to do is go back to the graph and show you that if we had that point there, that would be a diameter of 25.16579. Nope, I wrote the wrong number. Try again. So if you read the right number that I have here, it would be 25.0248. So you could see 0248. So you could see it's actually somewhere right around here because 02 is a little bit smaller. So you could see that this line is not quite right on my graph. You know, if you think about it, once you do the calculation, it would be about right there. And if you think about it, remember we have 95% here, right? And so you would have 2.5% on either side from the plus or minus 2 standard deviations. And you see 2.5% is actually less than 3. So you would think that it has to be a little bit bigger than the z value of -2. And you can see it is. It's 0.02478. So just slightly bigger than that. So that ends the lecture, the recorded lectures I have planned for section 7.2. I highly recommend that you take a look at the book, especially if you want to use your calculator. Let me show you a couple of those slides before I call it a day here, or call it a lecture here, and you find those. Let's see. That's the z-score calculation. There's the tables again. And here's the calculator. So the normal CDF is the norm.dist that I did in the spreadsheet calculation with regards to that. And given these calculations for a specific point, instead of norm.inv in the spreadsheet, you have inv norm in your calculator. So again, take a look at that if you want, figure out the right inputs for that. The book does a very good job of that. So that ends the lectures for section 7.2.